is chapter 4, and chapter 4 has to do with probabilities. What's nice is it's only broken into 3 chunks instead of 6, but they're pretty big chunks. So I remember learning about probabilities when I was a kid, like in 6th grade or whenever they kind of taught us the basic idea of it. And I was like, oh, this is easy. And then there would be like these more and more complex versions of it. And pretty soon it wasn't easy for me at all. And so it's been interesting for me. Like I said, it's been a few years since I took a statistics class as a student. And so in some ways I'm going through this as a student with you guys. I'm doing the homework and I'm making sure I'm comfortable with it before I come to class so that I'm not a complete idiot, because I'm not an expert in this. It's not something I do all the time. I use probabilities in my work, but I don't think of them in the context of a math problem. You know what I mean? I just think of them as a more commonsensical thing a lot of times. So hopefully this won't be... What I felt like as I reviewed this lecture and I reviewed the chapter is, so often as they do in math, they make this seem harder than it is. And so I fear a little bit that when we go through this lecture, you'll be like, oh, wait, what is that? But as you do the work, it's not too bad. Okay? So just hold on and we'll get through it. Of course, you can ask questions, but it's doable. Okay? There's a couple spots in it where you're like, wait, I have to think hard. I would recommend reading through the chapter, especially anything that really hangs you up. Again, I like the way the textbook's written. I think the author explains things pretty clearly. He's a good author. So let's just do this. So, an introduction to probabilities. A probability is a numerical range from 0 to 1, usually expressed as a percentage. And it indicates the likelihood of something occurring. If something has a probability of 0, it means it cannot occur. If it has a likelihood of, or a probability of 1, or 100%, that means it will absolutely occur. And then everything else falls between that range of can't happen to will happen, right? So that's the basic rules of probabilities. Some definitions they have in the textbook that hit you with right up front in bold terms. They just want you to know what these things mean. Okay? I won't insult your intelligence by reading them to you. You can read them there, and they're in your textbook as well. Actually, I will explain this. So sample space means all of the possible outcomes that could happen. So for example, if you were to roll a 6-sided die, your sample space would be a 1, 2, 3, 4, 5, or 6. Those are all of the possibilities that could happen. If all probabilities were that easy, then this would be an easy section, right? If you pulled one card out of a deck of cards, the sample space is 1 to 52. There's only 52 possible things that could happen there. All right, that's what sample space means. An event is another word for outcome when we're talking about statistics. And a simple event is an event with a single outcome. Their example they have is rolling a 5 on a single die. There's some sample space examples. If you flip a coin, the sample space is either heads or tails. That's the only possible outcome. Theoretically, it can land on its edge, right? So, but not really. Multiple choice question, then your sample space is A, B, C, D, or E. Inspect a product, it's either defective or not defective. So sometimes the first trick in dealing with probabilities is to identify the sample space. Because you could say, I'm inspecting a product. It could either be defective or not defective or kind of defective. You could start to come up with all sorts of like shades of gray there, right? Shades of, but really, from an inspection standpoint, you really want to know if it's something I can sell to my customer or something I can't. So it's either defective or not defective. So that's the challenge in business is narrowing the parameters of the things you're trying to understand. Because that's all probabilities help you do, is they help you understand. They help you make decisions. How likely is it that somebody's going to buy this product, or that this product's going to fail, or something like that? All right, so that's sample space. All right. So there are 3 methods for assigning probability. The one we're probably most familiar with, the one they teach us in 6th grade math, or 5th, whatever grade it is what's called classical probability. And then empirical is pretty close to it. It's related. And then subjective is just what it sounds like. It's subjective, right? we try to predict what the weather is, it's pretty hard for us to come up with a very concrete mathematical model for that. It's fairly subjective. So let's talk about each one. So with classical probability, we use that when we know the number of possible outcomes. That's, in other words, we're talking about rolling a die, we know exactly how many outcomes there could be. So that's when we use classical probability. The formula is the probability of A, or the probability that event A will happen, is the number of possible outcomes that constitute event A divided by the total number of outcomes in the sample space. So for rolling a die, getting any particular number, then your numerator, number of possible outcomes that constitute A in this case would be 1, getting a 5 on a roll of a die. There's only one outcome that could give me that. And my total number of outcomes is 6. So it would be a 1 in 6, whatever that comes out to as a percentage. 15%, something like that. Oh, they're going to give us that very same thing. So they define the event as rolling a 5. There's 6 possible outcomes in the sample space. Event A, rolling a 5, can happen only in one way. So we take 1, we divide it by 6, comes out with 16.7%. So that's classical probability. That's pretty doable, right? If they were all that easy, awesome. All right, it assumes that each event in the sample space has the same likelihood, right? When we get into a situation where each event does not have the same likelihood, it becomes more challenging, right? The set of events is collectively exhaustive. That means the sample space includes every possible event that could occur. So an example that might be a little tougher is, what if we were going to roll 2 dice? Right, with 2 dice, there's more than one way to get a 5, right? You could get a 4 and a 1, a 3 and a 2. So you would have more numbers in the numerator, and you'd have more numbers in the denominator now, because instead of just 6 possible ways, there's 36. And we'll talk more about that. Okay, empirical probability is a little bit different from the classical probability. It involves conducting an experiment to observe the frequency with which an event occurs, because you don't know the total number of items in the sample space. So for example, I think the example they give in the book is, if I want to know what percentage of customers that come in my store are going to buy something, I don't know exactly how many customers could possibly. It could be different on any given day. So instead, what I'll do is I'll set up an experiment and say, I'm going to observe the next 100 customers. And if they bought something, then I'll mark a little tick mark for bought, and if they didn't, I'll mark one for didn't buy. And after 100 people come in, I find out that 15 people bought something and 85 people didn't. That'd probably be a mall-type store with lots of browsers, right? But those are people who browse, not like Internet Explorer. Anyway, so as you can imagine, this is similar in some ways. The formula is the same. The frequency in which the event occurs divided by the total number of observations now, instead of the total number that could possibly happen. But this is imperfect, right? Because just because out of the next 100 people, 15 people buy something, doesn't mean that that'll be the same for the next 100. This is just an estimate. It's empirical probability. Empirical means it's based upon observation. Okay? Here's an example. 400 new graduates asked how much they owed in student loans. The results are shown in the following order. What is the probability that a randomly selected graduate has between $5,000 and $9,999 in student loans? So I would look at the amount. This is where the things we've already done come into play. This is just a frequency distribution, right? So if there was 102 who had 9,999, and there's 400 total, all we have to do to find the probability is divide it. 102 divided by 400, and that would give us the probability that the next person we ask would be in that range. Is it perfect? It's not, because this is just based on our observation of 400 things. But and as you can imagine, the larger the number of total observations I make in my experiment, the better this number will be, the more reliable this number will be. All right, so what is that? 102 divided by 400. Does anybody have a calculator that could easily do that? It's close to 25%, right? 25 point something. What, 25.25? 25.5%. All right. Again, that's pretty common sense if you're looking at it, right? About 1 in 4. What is the probability that a randomly selected graduate has $20,000 or more of student loans? So now I would have to take this amount, 66, and this amount, 47, right? Because all of that constitutes the range I'm looking at. So that should be 113. So there's 113 students that have 20,000 or more. Divide that by 400. That'll give me my probability. 28.25%. So that's empirical probability. The difference between classical is in classical you know how many possible outcomes there are, and in empirical you don't. So instead you have to base it on an observation of a certain amount. And it gives us our answers that we just worked out. I got a new clicker thing. Pretty awesome. And it's got a laser. Fancy. I know they've had these since 1980, but this one's mine. All right. All right. So something that happens is the law of large numbers. I mentioned this just a minute ago, that when an experiment is conducted a large number of times, the empirical probability of the process will converge with classical probability. And here's an example. If I flip a coin a large number of times, the observed number of heads will be very close to 50%. So with the flip of a coin, the chance that you can get a head would be 1 out of 2 possible chances, right? 50%. That would be the classical probability. But let's say I wanted to do an empirical study and I flipped a coin. I could have a head, and it wouldn't be crazy if I flipped it again and had heads again. And it wouldn't be that crazy if I did it 3 times in a row, right? Maybe even 4 times in a row. If I did that, let's say I flipped it 4 times and I got 3 heads and 1 tail, I could say the empirical probability would be 3 out of 4, or 0.75, that I was going to get heads. But I know the classical probability is 1 out of 2, or 0.5. Would I expect, though, that if I went from 4 flips of the coin to 100, that I'd be pretty close to 50-50 at 100, or closer, like maybe 45-55 or something like that? What if I did 1,000 or 1,000,000? So this law of large numbers says that the more times you run the experiment, the more the empirical probability will converge with the classical probability. That over large numbers of samples, we're going to get closer and closer to the mathematical truth, I guess, is a way of putting it. Which, again, I think is pretty logical. We see that even in gender of people, right? There are roughly 50% males and 50% females in the world. And that's with a population of 7 billion people. That's a pretty large number. And so we're pretty close to that. Now, there are factors that affect that. We know certain countries practice selective abortion and things like that to have more boys or fewer girls, things like that. So there is human intervention, but from just a purely chance standpoint, we would expect that our classical probability would be 50% male, 50% female. And then our big experiment, so to speak, with all of us having babies, it works out to that when we have such a large number, which is nice. It means you can find someone to love if you want to. The last one is subjective probability. I'm sure if I'd said that at a big university, I would have just been labeled homophobic right there. You're saying that the only possibility for people to find love is to find someone with the opposite sex. My bad, I guess. I don't know. I have the certain weakness in me. I have opposite gender attraction, and so I tend to assume other people feel the same way, even though I know not everybody does. So if I offended anyone, I apologize. Subjective probability. Methods of assigning probability, and then we already talked about classical and empirical, so there we are at subjective. So this is used when classical and empirical probabilities are not available. In other words, when you don't know, but you can make an educated guess, such as the probability that inflation will be greater than 4% next year, I would probably not be able to make a very good subjective analysis of what the probability is that inflation will be greater than 4% next year. I might be able to do a better subjective analysis of that than you would be able to, because I have more experience with markets and finance than most of you do, but probably not as good as an expert economist who studies inflation and writes articles for it in peer-reviewed journals all the time would have, right? So that's the nature of subjective things, is there's so many factors that we can't accurately mathematically forecast it. So you try to find an expert and say, what do you think is the likelihood that this is going to happen? And they'll start to base it on a number of factors and say, yeah, it's pretty low. I'd say less than 10%. Can you pinpoint it? I'd say 4 or 5%. That's what subjective means. It's not hard science. It's an estimate. And the better your expert, the better your estimate, right? All right. So here's the little review. Basic properties of probability. These are in the textbook as well. Number 1, if probability of 1, then there's certainty that the event will occur. That means 100%. If you have a probability of 0, then with certainty the event will not occur. Rule 3, the probability of any event must range between 0 and 1. So if something is greater than 1, that can't be a probability. If it's less than 0, also can't be. No negative numbers. Number 4, the sum of all probabilities for simple events in the sample space must be equal to 1. So for example, the likelihood that I would roll a 1 plus the likelihood that I would roll a 2 plus the likelihood that I would roll a 3, 4, 5, and 6, all of those together will add up to 1, right? There's a 100% chance that I'll roll a 1, 2, 3, 4, 5, or 6. That's what that means. Rule number 5. The complement to event A is defined as all of the outcomes in the sample space that are not part of event A. The complement is denoted as A with a little apostrophe thing. There's probably some Greek name that I don't know for that. But in other words, if I were to take the probability that I would roll a 1 and add it to the probability that I would roll a 2, 3, 4, or 5, the 2 would add up to 1. The probability that I would roll a 1, 2, or 3 plus the probability that I would roll a 4, 5, or 6 will add up to 1. That's what I mean by the complement, that all of the probabilities together in the sample space will add up to 1. All right, so that was probability rules when we're dealing with one event. What happens if we're having more than one event, more than one outcome? This is where we use the contingency tables that we learned about in, was it chapter 2 where we started with contingency tables? Remember Excel called them pivot tables? Okay. They're nice because they show you how everything adds up with each other. So this is 2 events from a deck of 52 cards, meaning we're drawing, in this case the event is drawing a card. So we're drawing 2 cards from the deck. And I guess the event A is the card is an ace. And event B is the card is a red one. So what's the chance of pulling an ace from the deck? It's 4 out of 52, right? That's the probability, whatever that number comes out to. It's less than 10%, about 7.5%, something like that. What's the probability that a card would be red? 26 out of 52, or 50%. So now the question is, what's the probability that the card be a red ace? Right? That's what we're trying to figure out. So this is what I just mentioned. Chance of having an ace, 4 out of 52, or 0.077, or 7%, 7.7% of the cards in the deck are aces. The chance that it's red is 26 out of 52, or 0.5%. See, do you see how the contingency table makes this easier, for me at least, to look at it? I like things in table format. What I like about this book is they'll show you the crazy long formula, and then they'll say you can also use a table. And I'm like, that works better for my brain. There's people who are formula people who like formulas. I like the tables because I like Excel, because I think it's wonderful. All right. But we're interested in the intersection of events A and B. In other words, here we had event A, 4 out of 52, event B, 26 out of 52. What about the intersection where those two things cross into each other? The event A and B will occur at the same time. And watch the language. They even have it bolded, A and B, because in a minute they're going to talk about, well, what about A or B? Which is different, right? So what's the chance A and B both occur? So the probability of having a red ace is going to be 2 out of 52. Does that make sense? It's where the two intersect on the contingency table. If we think about it logically, we probably could have come up with that without seeing it on the contingency table. How many red aces are in the pack of cards? 2. How many cards total? 52. All right. So we're getting a pretty small number there, 3.8%, that any given number will be a red ace, or any given card that you draw. Sometimes they denote this and this way. It's a little upside down horseshoe thingy. That's the technical term for it. All right, the union of events is represented when the number of instances are either event A or event B occur, or both events occur together. So consider the union of ace or red card. What's the chance that the card I pull will be either an ace or a red card? You could be tempted, if your brain works like mine, to say, well, I'll just look at the red, 26, and the ace, 4, and I'll add them together, and I'll come up with 30 possibilities out of 52. If you do that, you'll be wrong, because you'll be double counting where they overlap each other. So there's two ways of doing it. One way is to just look at all three and add them up, 24, 25, 26, 27, 28. There's 28 possible choices out of 52 that would be either a red or an ace. Or the other is to take the total of the reds, the total of the aces, and then subtract the overlap, where they overlap the red aces. That would also come up with 28. All right, so that's a union. I think it's easy to remember the denotation because here the horseshoe thingy is the other way. It looks like a U. That means union. All right? You can come up with whatever you want, but that's how I remember it. All right, the addition rule for probabilities. This is used to calculate the probability of the union of events. So the probability that event A or event B or both events will occur. Two events are considered to be mutually exclusive if they cannot occur at the same time during the experiment. For mutually exclusive events, the addition rule states that the probability of two events occurring is simply the sum of their individual probabilities. So the probability of A occurring plus the probability of B occurring will give us the probability of A or B occurring. This is when they're mutually exclusive, meaning they can't happen at the same time. When they are not mutually exclusive, now it's the probability of A plus the probability of B minus the probability of A and B. So let me take you back to our contingency table. The probability of A was 4 out of 52. The probability of B was 26 out of 52. These cards, in some cases, are not mutually exclusive. So what we have to do is subtract the probability that it could be an ace and a red. So that's what they mean by that. When they can, maybe an easy way to say that is when they can overlap each other, you have to subtract out the ones that can overlap so you don't double count them. I think they use these terms like mutually exclusive. It can get confusing in our brain because we don't use those terms all the time. But that's all it means. So in the case where you have two events that can't overlap each other, then it's just the probability of A plus the probability of B. And in the case where they can overlap each other, it's the probability of A plus the probability of B minus the place where they overlap, the probability of A and B. So the ace of the red card, that's what I just mentioned. So it's 4 over 52 plus 26 over 52 minus 2 over 52 gives us the 28 over 52. Everybody makes sense that this overlap here can be, it's easy to double count that when you're trying to figure out the probability. That's what they're trying to hammer on that, the author who wrote this little slideshow. And they show it to you again. Don't count the common elements twice. Apparently this must happen a lot because they really are hammering on it. All right, conditional probability. Conditional probability is the probability of an event occurring given the condition that event B has occurred. So here's their example. We have SAT scores, and then we have students who took a prep class and students who took no prep class. I guess I could point at it with my laser. Awesome, right? So here we could see, like, you could ask questions like what's the percentage that any given student would score a 601 to 800 on the SAT score? And the answer would be, it would be 42 out of the 250. That's how many scored in that range, right? This would be an example of empirical probability, right? Because we don't know how many people total took the test. This is the number that are in this sample that we've observed. So 42 out of 250. But then the question is, okay, so if they took a prep class, did that improve their chances, improve their odds, improve the probability that they scored higher on the test? That's a fair question. And we want to ask those questions all the time in business, right? If they saw our advertisement, did that increase the likelihood that they bought our product? Something like that. We want to know that. All right. So here's how it's denotated. That means given that event B has occurred, what's the likelihood that A occurred? There's a couple ways to do this. I think my way is a little easier than theirs, but they set theirs up. So what they're saying is the prior probability, that's the idea that 42 out of the 250 people scored a 601 to an 800. We can calculate that as 0.168. But if we want to know the ones who took the prep class that scored, we would say that is 22 out of 70. Do you see how it reduces the denominator of the problem? Because we want to only consider those people who took the prep class. So 22 out of 70 who took the prep class scored a 601 to an 800. Or there was a 31.4% probability that if you took the prep class, you scored in that range. Whereas if you didn't take the prep class, so the whole population, including those who did take it and those who didn't, they were 42 out of 250, or 16.8%. So the reason we want to compare those two things is we're asking ourselves, does the intervention of the prep class make a difference? And in this case, it seems like it clearly does, right? Students who took the prep class, they scored high on the test at a rate nearly double the general population. And by general population, we mean everybody, the ones who took the class and the ones who didn't. Does that make some sense? Or no? We're asking conditionally, if you took the prep class, what was the probability of you scoring 601 to 800? And it was 22 out of 70. Then we're asking, out of everybody, what was the probability of scoring in that same range? And it was 42 out of 250. And that comparison lets us see that taking the prep class in this case seemed to have a pretty marked effect on increasing your probability of scoring high. There's their formula for calculating conditional probability. So the probability of A and B divided by the probability of B, or the probability of A and B divided by the probability of A, depending on which one you're trying to find. A conditional probability is also known as a posterior probability. Posterior means at the back of something, right? like your mom used to kick you in your posterior, right? Which is a revision of the prior probability using additional information. Or in other words, let me put that in a little easier context. It means if we're comparing it and saying, how is this different than what the whole group is? Because now we have additional information to consider, like part of this group took a prep course. We want to compare it with that. So it's all the same numbers, right? We never changed the numbers to find this out. We just said, given B, given that they took the prep class, what was the probability that they achieved A, which was a high score? Whereas our prior probability was, what was the probability they achieved a high score? So you're kind of factoring in this additional item, in this case, the prep class. There, they're just showing it the other way they could work it out. Probability of A and B is 22 out of 250. The probability that you had both the prep class and a high score was 22 out of the total of 250. The probability of B is 70 out of 250. So they took the probability of A and B, divided it by that, and it comes out to the same answer. So I like the way of just looking at, to me, the easiest way to find the prep class high score is to just say 22 out of 70. But you can say it's 22 out of the 250, and it's 70 out of the 250, and you can divide them out, and it comes out to the same answer. So they're showing you two different pathways to the same answer. And if one clicks in your brain better than the other, then use that one. They're both right. All right. When we're dealing with probabilities, some events are independent of one another, meaning the occurrence of one has nothing to do with the occurrence of the other. Other events are dependent, meaning the occurrence of the one might lead to another or may impact the occurrence of the other. A good example would be if I pull a card out of a deck and I want to say, what's the likelihood on the second card I pull out? I have to remember there's not 52 cards in the deck anymore, there's only 51. So it changes, the drawing of the first card changes the probability of the drawing of the second card. Does that make sense? Because one's dependent on the other. So we're not talking about causality. We're talking about a related thing. They're dependent. Here's our formula for determining if events A and B are independent. And so the probability that B given A equals the probability of A, if those two things equal each other, they're independent. That one's confusing. And it's one that as you work it out a couple times, it'll start to be more evident what that means. Okay? If the probability of B given A does not equal the probability of A, then the events are not independent. I'm just going to move on from that. You'll see it when you work it out. Here's their example. Event A is a grade of 80% or better. Event B is interested in the subject. Our question would be, are these things dependent on one another or are they not? We would probably guess that they're dependent, right? That students who say they're interested in a subject are most likely going to be scoring higher than students who say they're not interested in the subject. And that's how a lot of this is. They get all confusing with it, but when you think about it, there's usually a common sense relationship. In fact, the only thing that really makes good papers for getting published is when you have this assumption that's common sense based, and then you do a study and it turns out that that's not how it is. And that's when people are like, oh, that's an interesting finding. Because the rest of the time, we would expect students who are interested in a subject to score higher than students who are not interested in a subject. All right, so here they've done a contingency table. They found that in this particular situation, out of 114 students, 72% who said they were interested, not 72%, 72 of the 114 that said they were interested scored 80% or better. 42 of the 114 scored less than 80%. Over here, people who said they're not interested, 38 out of 86 scored 80% or better. 48 out of 86 scored less than 80%. So we're testing to see if they're dependent or independent. So again, we take the probability that B happens given A, which is 72 out of the 114, or 63%. Then we take the probability of A, which is 110 out of the total of 200, which is 55%. Since they're not equal to each other, we're going to say that they are dependent. So it's just a simple test, okay? Don't get your brain too wound up in what it all means yet. It'll start to be clearer as you do some problems with it. Multiplication rule is used to determine the probability of the intersection or the joint probability of two events occurring. P, A, and B, that's the intersection. Formula for the multiplication rule for dependent events. There you go. They're spelled out for you. Again, I would tell you to use the book. The book gives you some tabular ways, table ways of working these out that I think more clearly explain how they all interconnect. Because as I read it at first, I was like, this is confusing. And then I looked at the table and worked out the table and was like, oh, well, that's not so bad. There's their example for dependent events. Event A, rain is forecasted. Event B, people will carry an umbrella. Our assumption that gives us some numbers here. The probability that rain is forecasted is 30%. And the probability that if rain is forecasted, people will carry an umbrella is 90%. So the probability A and B is just multiplied. And like I said, when you work these out, you'd be like, oh, this is way simpler than I thought. I take probability of one, 0.3, multiply it by the probability of the second one, 0.9, and I come out with 0.27. So 27% probability that it will rain and you'll carry an umbrella. I wish I didn't have to lecture on this. I wish we could just get right into the work. But I think introducing it will still have value, because when you get into the work, you'd be like, okay, this is kind of the stuff we talked about, even though I know it feels a little confusing right now. Same thing. PA times PB. When multiple events are all independent, the probability of them all occurring is simply the product of their individual probabilities. So if we say the probability of event 1 happening, or event A happening, and the probability of event B happening, what's the probability they'll both happen? It's just A times B. If there's 4 different events, A times B times C times D. It's just the product. You just multiply it out. And if you think about that, if all of these probabilities are between 0 and 1, the more events we add, the more we're multiplying by each other, the lower it's going to drive that number, right? And then that makes some logical sense. You know, the likelihood that two things will happen is less than the likelihood that just one of the two things could happen. The likelihood of 4 different things all occurring is going to be less than the likelihood that any one of those 4 occurring individually would be. Because we're saying that we've got to have this sort of additive relationship between the two. So it's more logical than I think their formulas make it out to be. So now they're just telling you kind of what we've already seen, that we can do a contingency table that will convert frequencies into probabilities. In fact, I think there's a function on the pivot table where you right-click on it and you can show it as a probability. And if you think about it, all it's doing is saying, you know, so interested, 80% or better. If you divide that 72 by the 200, that gives you the probability. And now the whole table shows you the probability of any one event occurring, the simple probabilities, or of both events. Like that. And in my mind, that's a lot easier to think about than that. But I'm not a mathematician. Another way they show it is what's called a decision tree. When we do the decision tree, at any point, our probabilities are going to add up to 1. So in this case, is this the same example? Probability of A is 55%. Yeah. So the probability of A is 55%. Probability of B then is 45%. If A happens, and A stood for scoring an 80% or better, then the probability of B, that they were interested, is 36. Not B, or not interested, is 19%, which is broken out here and here. So that's another way to look at it. Again, this way worked for my brain. It was a logical flow, and that helped me see it a little bit better. All right, Bayes' theorem. So Bayes' theorem was meant to come up with a way to kind of find a, he found a mathematical way to represent the relationship between all of these probabilities. Suppose two events have prior probabilities, PA1 and PA2, probability of A1 happening or probability of A2 happening. Let events A1 and A2 be mutually exclusive, right? They do it all in math. All that he's really saying here, let's show an example. So here's the formula for Bayes' theorem. I think it looks really confusing. Let's look at the example. PNC Bank classifies its credit card customers into three categories by their credit. 600, 600 to 700, or more than 700. Define B as follows. Event B, customer is late on his or her current credit card payment. Suppose we have the following historical information. Customers with a credit score of less than 600 are late on their payments 40% of the time. Customers with credit scores between 600 and 700 are late with their payments 10% of the time. Customers with credit scores of more than 700 are late with their payments 5% of the time. So now we take this big complex formula, Bayes' theorem, and really all it's saying is the probability of A, which was 25%, okay, times the probability of A occurring given B, which it actually told us here. So the probability of A1 occurring given B, 40%. Let me get back to it. And then you divide that by the probability of A1 times the probability of A1 occurring if B, A2, A3. And again, it's kind of like this. It's kind of like the mean where you looked at that big formula and you're like, this is really complex. And then when you think about it, it's just the sum of each of these events on the bottom. And then you just do the math. In a table form, it's even easier to see. We have the prior probability, the conditional probability. We multiply those to get the joint probability. We take a sum, and then we divide the joint probability by the sum. That's it. So it sounds more complicated than it is. And it is very complicated. But the math doesn't have to be that hard. When we do some examples, it'll come clearer why we're doing that. Okay? All right, last section. I know it's been a painful one thus far. I could tell by how quiet you guys all are that you're like, oh, I've tried to make this process in my brain and it seems confusing. All right, the fundamental counting principle. If there are K1 choices for the first event and K2 choices for a second event and Kn choices for the nth event, then the total number of possible outcomes are K1, K2, K3 to the Kn. Or not to the Kn, but continuing on. Again, that's really confusing. All it really means is, and what we're using this for is so we can figure out how many possible outcomes we have so we can figure out probability. So, for example, suppose a 3-digit number is to be selected using an initial letter A, B, C, or D, followed by two numbers 0 to 9. How many different model numbers are possible? Okay. So, if we use this little formula, the first one we would say there's 4 choices, right? If the first letter is an A, B, C, or D. So K1 is 4. Then if it's number 0 to 9, there's 10 possibilities. So we'll use the number 10 for K2. And then there's a third digit, which is also 10, because it's another 0 to 9 number. And what they mean by this ... Kn is that you could keep, if it was a 20-digit serial number, you would keep extending each of those out until you had each digit represented. So how many possible choices are there in that case where we have a 4-digit followed by a 10-digit followed by a 10-digit? We'd have 400 possible choices. So we would use this in business when we're figuring out things like serial numbers, right? How many do I need to create? How many digit number do I need to have so that I can know that my number, I can have a unique number for every one of my products or something like that? Or also for finding out probability, like how many choices are there in the denominator? Well, if there's 4, 10, and 10, then there's going to be 400 total choices. So this is called the fundamental counting principle, and it helps us figure out how many possibles we have or possibilities we have. A related concept are permutations, the number of different ways objects can be arranged in order. Again, this is confusing looking. Like there's an exclamation point in math. Why? This makes no sense to me. Okay? But all the exclamation point means is that you take the number, multiply it by the number minus 1, by the number minus 2, and so forth till you get down to 1. Okay? So for example, well, no, they're not giving us an example. Formula for the permutations of n objects selected n at a time. And so in this case, if we were going to say like, hey, well, let me just go through this, and I'll give you some examples tomorrow so we can get, I want to make sure we get there on Wednesday, make sure we get through the little slideshow, and then we'll get into examples. Formula for the permutations of n objects selected n at a time is n with the exclamation point over n minus x, exclamation point. They're going to give us an example. Okay, suppose that the two letters are to be selected from A, B, C, and D and arranged in order. How many permutations are possible? So we would say 4 with an exclamation point means 4 times 3 times 2 times 1. Okay? And then if we're pulling them 2 at a time, it's going to be 4 minus 2, which is 2, which is 2 times 1. And that gives us 12 possible. And then you can test that in this case by writing out all the possible permutations, and it comes out to 12. Okay? Combinations are similar, except they don't care about order. And so it's a similar formula. Suppose we have two letters that are to be selected, A, B, C, and D. How many combinations are possible? When it says combinations, that's a way of saying order is not important. The number of combinations is 4 over 2, still 6. But here, when we say that the order is not important, we recognize that B and C and B are the same thing. As opposed to in permutations, we say the order does matter. B and C and BC and CB are two different choices. Okay? That's the whole thing. I promise you it is not as scary as it sounds. And so the best thing we can do is get into some examples of it on Wednesday. And once we get doing that, it will go pretty easily, I think. All right? Have a good day. I always hate it when the lecture makes people more afraid. Although I'm guessing if everybody had read through the chapter before they came here, they might be less afraid. But I can't control that part. See you guys. Whose birthday is it? Happy birthday.